All right, thank you and welcome everybody to our June meeting. Today we have a great meeting in store for you. We have our speaker today is Martin Matson. He is currently working with the data platform analytics team at Allegiant. He is a PhD in physics from the University of Michigan, and he's going to be showing us today or walking us through a solution built with the Cortana Intelligence Suite that will demonstrate how to build a data science solution that predicts the gas of price. So we'll keep the intro short today. So without further ado, I'm going to go ahead and make Martin the speaker. And Martin, please take it away.
All right. I don't have screen sharing yet here. Oh, there we
Okay,
go.
you should have it now.
All right. Have you got my screen now?
Yes, we can see it.
Okay, great. Thanks for the introduction, and hopefully we can step through what turns out to be a kind of a fun little model. Um, The idea behind the model was to develop a predictive model for an industrial consumer, for industrial customer, a company who has some kind of input. They have input prices, something, the goods that come in, imports and exports perhaps that play a role in their material stream, perhaps some online inventory or some inventory that they have or their competitors have, and then how much production they are capable of. And it turns out that the oil industry has all of these pieces, and even better yet, there's a publicly available database that gives access to sort of weekly United States aggregate data for all of these pieces, including the price of gasoline averaged across the entire country. So the idea is to put together all these pieces into this predictive model and then show that we can make a dashboard showing, sort of given the state of everything that's going on this week, what would the price of the output be next week so that we can make decisions based on the future price. So the model begins with web table data from the U.S. Energy Information Administration. I'm actually using 6 different web tables. There's a variety of ways that we could export this data. It turns out that the most straightforward way was just to pull it off as a web table and then process the data just manually. So just to give you an idea of the kinds of things, every week they publish the average retail gasoline prices, and then every day they have the spot price for crude oil published from Cushing's, Oklahoma. It just turns out to be the standard way of measuring the spot price of oil. So the general idea is to start with that data and then use the Azure Data Factory pipeline to pull that in. And I'm just storing it as tables as an Azure blob for now. The data is not really ready for storage in a SQL database, so that's the first step. And I'll show you sort of pieces of the Data Factory pipeline as we go, but this is the picture, the overview of the whole entire pipeline. And starting off on the left-hand side, we're starting with a handful of data tables that we pull off the internet, and then we use the web table to Azure Blob pipeline activities to pull those in and to store them all as blobs on Azure Blob Storage. And this is what the data looks like. Again, it's not clean enough to do anything real with it yet, but it's and I have 7 or 8 of these, and they all need to be joined together. And that's sort of a classic use case for doing this using Apache's Pig on the Hadoop cluster. So Pig can feed these in really straightforward and do the data transformations, the joins in a straightforward way, and it does it as a batch. Since I only have to worry about doing this once a week, I can just set up a batch process to do this weekly. So that's the next step. I'm going to have the Data Factory provision an HD Insight cluster, and it's on demand, so it only boots up when I need it once a week to do the clean and the processing and the joining of the data. And then I wrote a simple Pig script to take in all those 8 data tables and process them and clean them up so that I can use them for the machine learning. I actually am having Pig spit out 4 different data tables, and this comes from, in part, the needs for the machine learning training. In order to do the training, I want to have the features and the gas prices as separate pieces so that I can train based on the other inputs, the price of the crude oil and the amount of gas stores there are, the imports and the exports, and then use the gas prices, the historical gas prices, as the data labels, and use that to train the model. Then, in order to know whether or not the model was working, I wanted to take something like the last 6 or 8 months worth of data, which is not a lot when you're only polling weekly. But I take the last 6 or 8 months worth of data and I store that aside as the recent features and the recent prices, and use that to test to see whether or not the model is working. And it gives sort of an idea. If I had put this model together, 4 or 5 months ago, I would have been able to predict with reasonable accuracy. How good can I predict the gas prices for the coming week? The pipeline is actually still running, and so it pulled in the data from last week, and so we'll take a look at the current status of the model. So this is again what the data looks like coming out of the Pig scripts. I have internally, I keep track of what all the columns are and what they mean. That's probably the most important part as I go, because the Hadoop Pig doesn't want data labels, and it doesn't want that kind of stuff on the columns, so I just keep them unlabeled data structures. So the next part, now that I have the training data, I need to sort of step aside from the data factory pipeline and go into Azure Machine Learning, use the online Machine Learning Studio to develop a model to make predictions of the gas prices. And this is what it looks like from Azure's Machine Learning Studio. I have 2 sets of imports. I have the historical features and then the historical gas prices. And edit the metadata, which gives the columns labels so that I know what I'm dealing with, and it sets the types to the columns. Then I join the data in together. I join it on date, and then select out everything but the date so that I can send that to the model to train. I'm using a boosted decision tree regression, and I'll talk about that a little bit later as to which model turned out to be the best at predicting the dates, predicting the gas prices for next week. And then I score the model to get an idea of what the model would have predicted would have been the historical gas prices. And I'll show some of those a little bit later as well. Once I have the trained model, I deploy that on the Azure Machine Learning Studio as a web service. So now it knows how to take any incoming features and make a prediction as to what the gas price would be. So the idea is that I can pull off next week's inputs, the imports and the crude oil prices, and what week of the year it is, and then send those to the machine learning web service, and it will tell me what the gas price will be next week. This is what the trained model looks like. It's very similar, except it only has one input. It doesn't have the scores, the gas prices, because I don't know what the gas price is going to be next week. So we import the data in a similar way. We added the metadata to make the same kind of columns. This one, I actually pull off the date column because the date column isn't part of the model training, and so I have to pull it off first, and then I have to add it back again at the end so that I know what data I'm dealing with. And then I have a web service output. This actually is importing data from Azure Blob Storage. So there's a pointer from the machine data factory pipeline that tells me where to get the data from when I'm sending it to training the trained model. So once I have the model trained and deployed, then the last step is to make predictions on the current data. And so that's the last, it's actually the second to last activity in the data factory pipeline, is to take the data output from Pig and send it off to be scored so that I can make predictions, making the predictions on the model. So that's this section of the pipeline, sort of in the middle here. The other stuff above and below I'll talk about in a little bit, but basically in order to get the data off of Azure Blob Storage in a usable form, it was much easier to put it into the SQL Server. And so I have activities in the pipeline that will take those data tables and send them over to SQL Server, which just makes it a lot more straightforward to interface with Power BI. So again, as an example of the kind of data that are coming off of the predictions from the machine learning, so instead of gas prices, I have scored labels. And so that far right column on each one of these tables is what the gas price is predicted to have been that week. And then I can compare that to the actual gas prices to see how the models worked. And then, like I said, the last piece here is to deploy the results to the SQL Server. So what I've ended up with is a model that will take in the inputs from a variety of different places and then make predictions on them. And I'd like to be able to present that to an end user, somebody who's making decisions based on the status of the industry, based on the status of what's happening, as to how much they want to produce or how much they want to ship out or store. So it was natural to take that and to put it in as a Power BI dashboard. And I'm going to switch over to the live dashboard here and take a look at what I've got. Let's see, I'm just going to do that. All right, so this is the live Power BI dashboard, and what I've put together is sort of a decision maker's dashboard where we've got a handful of inputs so that we can monitor, the end user can monitor what's happening with the industry, and then a handful of outputs to take a look at what's happening. And I'm actually going to go to this report as opposed to being on the dashboard. And then I have a filter set on the Power BI report so that I can pretend like it's a different week than it actually is, because I have sort of historical data and then I have predicted data from the last 6 months or so. I can ask the question, what would this be like if there we go. What would this be like if I were actually sort of the January 1st, 2016? So what I'm going to do is just kind of pull the data back and look at historical data from sort of middle of 2013, and I'm going to end looking at the historical data sort of the start of 2016 or so, and then we'll come back and look at where the data looks like at the very end. It's not going to let me pull that over. All right, there we go. No, maybe. So it lets the user build a window here. This will work. And then based on that window, it updates the other visualizations. So I can see that over the course of the last 2 years, there's a seasonal aspect to the supply of gasoline. I can look at the oil imports. The green data is the data that I used for model training. And then the black data is data that got used to predict the output price of gasoline. So it wasn't data that was used in the training model. So you see that there's some randomness to some of the data, but there are a handful of patterns. And then on the right-hand side, what I've got on the dashboard is something of this was the actual gas price on April 15th this year. The actual average gas price. And then what the model is predicting is that the following week, the gas price will actually increase about 30 cents to $2.34. So the model is predicting an upturn in the price of gasoline for that following week. So given one piece of data, this is predicting the next. Now, because this is actually historical data as well, we actually know what the price of gasoline was that following week. The actual price of gasoline that week was $2.16. So it turned out that the direction of the prediction was correct, even though the magnitude of the prediction wasn't. But the idea is that now the user can sit and look on one dashboard, except for the actual gasoline price for that week. The user can see what would be the direction and how much to expect for the changes in the output prices. And I guess I'll keep going and talk about the model and the machine learning side of this thing, but then if you have questions at the end, we can come back and step through sort of what each of these pieces do. If I extend out the time till the end, I don't know, it's going to let me extend the time to the currently. I can tell you what the prices of gasoline were predicted to have been. There's probably a tense issue there last week. Let me slide that over. For the May 9th, looks like that's about as close as it's going to let me get for predictions. All right, so we'll come back to that if there are questions at the end. So that's the general idea of how creating sort of an end user portal for the data output. And the Power BI is pulling this from the SQL Server tables, which are getting updated weekly as the model pulls the data off of the web tables and puts it back onto makes the predictions and puts it on the SQL Server. So I want to talk a little bit about what machine learning strategies I used and why I chose to use the boosted decision tree regression in the end for this particular model. The first step I usually take when doing machine learning is to look for patterns in the data. In some ways, I think this is slightly cheating because this is using eyeball learning as opposed to machine learning. But because we have this particular example is scored data, I can look at the input values as a function of the output value that I know about, the gas price, and look for patterns. And so on the left, what I've got is gas price along the horizontal axis, and then I take all the different data tables that I've got coming in. I did this particular investigation I did using analysis packages in R, and there's actually a really nice package notebook capability now in Azure Machine Learning Studio that you can actually start R notebooks right in the Machine Learning Studio and use data that's already there and work with it. So that's what I ended up doing. It's a nice interface, and it means that the data and the analysis are all in one place together. So looking my eye at what's going on with these different pieces, I can certainly see that there are fluctuations and patterns in the data, and that's a good starting point to say that there's a possibility of doing machine learning. If it all looks like just noise, it's still possible that there might be hidden patterns, but certainly having linear trends, for example, in the second plot down, there's a nice linear trend. Crude price and the gasoline prices are fairly well correlated. There's also a fairly nice trend in the gas stock that as the gas price goes up, the gas stock goes down. So it's a fairly well correlated situation, which means that this is going to be certainly amenable for doing a fit, making predictions on the model. I also look at the correlations between the features. Just to see if there are several features that are very highly correlated, it might mean that I don't need to use both of them. And early on in the process, in looking at the data, I found several other features that were very highly correlated to what I have here. And so I actually eliminated several different data sets because they weren't providing anything additional to the model. The only two data points that are highly correlated right now are the crude price and the gas stock, and they're actually anti-correlated. As the crude price goes up, the gas stock goes down. But it's not a perfect correlation, and so I chose to leave both pieces in the model, the predictive model. So at this point, I turn to the Azure machine learning cheat sheet. The URL for this cheat sheet is actually at the very bottom of the poster. This is a great place to go to get started in terms of thinking about the different types of models that could be used. I'm certainly in the regression regime. I have scored data labels, so this is machine learning with known outcomes. It's supervised learning. And because I'm looking at a continuous output, it's not classification. That means that I've got a regression model. So the question is, which of the regression models should I start with? And it almost always makes sense to start with a linear regression just to see how it works. It's the most forward solution. It's the fastest training solution for a regression. And if it works, then great, I'm done. So I started there. And I'm going to look at two different pieces. I'm going to look first at the performance of the model in sample, the performance of the regression, where I take a handful of the initial training data and I store it aside and use it to test to see the performance of the model. I think I'm doing an 80-20 split on my training data. Then that gives me an idea in sample as to how the model is working. So you can see on the left, I sort of plot this versus date, and I'm using data that goes all the way back to 1995. And that for a reasonable amount, the sort of reddish line is the prediction. The green dots are the test points that I didn't use to train the model, and then the blue points are, the blue line indicates the points that I used to train the model. And so you see that the prediction is following for the most part, it's following the shape of the actual training data. And then I can take the green points, because they're part of the training data, I can actually check the predicted price and the actual price against each other. If this were a perfect model and where I were perfectly predicting the outcome of each point, then this would be a perfectly straight line with a slope of 1. And so you can see that it's not, but it's not doing too bad. For the most part, the actual price and the predicted price are fairly correlated to each other. And what I do is then just do the root mean square of the deviation for each one of them. I take the difference between the two, square it, add them all up, and take the square root. It gives me a fairly straightforward measure as to the quality of the overall fit. And the smaller that number is, then the better the model is working. So the root mean square, the RMS deviation for this particular model, this is just a simple linear regression, was about 15 cents. So if I average how far off I was in the predicted versus actual price, it's about 15 cents, give or take, which is not too bad, given that the price of gas across town in any given place could be 5 or 6 or maybe even 10 cents. So to be 15 cents off is not that bad in the prediction. So because I stored a set of the data to play around with so that I could check the accuracy of my model, I can now take that model that I trained on the training data and say, all right, how well is that working at predicting the prices of gasoline in this window? And then the window I chose was basically from the sort of September 2015 to now. And you can see that the prediction, which again is in the light red, the prediction is following what's actually happened reasonably well. It starts to get off sort of early January and ends up being a little high through the rest of the 2016. But that's not too bad, given that it was just a very simple linear prediction model. And you can see the RMS deviation for the actual price versus predicted price turns out to be about 9 cents. So it's actually doing slightly better on the test data than it was doing on the training data. So that's okay. I wanted to see if I could do better. So it's back to the algorithm cheat sheet to see what other possibilities are there. One of the possibilities that's not in the base Azure Machine Learning Studio is the support vector machine regression. They actually have a support vector machine classifier in there, but they don't have the regression version of the SVM. But it's actually a straightforward model to implement using R. And if I wanted to implement it using the Machine Learning Studio, you can actually implement R machine learning algorithms in a very straightforward way as part of the Azure Machine Learning Studio. So because it's an easy algorithm to implement in R, I'm going to show what happened when I looked at the support vector machine. I actually used the radial basis kernel, which means that it's now a nonlinear model, which hopefully gives me the capability of doing better predictions. So again, back to the training data and training the model, you can see that the prediction is now following the model a little bit better. And in sample, the performance is significantly better. For comparison, I have a little picture of the linear models in sample performance, which had an RMS deviation of about 15 cents. And the support vector machine regression has an RMS deviation of only 1 cent. So it's about 15 times better at performance in model, which is great. The nice thing about SVM regressions is that because it's nonlinear, it can handle more hidden pattern stuff that we just can't necessarily see by eye. So it doesn't surprise me that it did better in sample performance. However, the other shoe drops. When I looked at the out-of-sample performance from the support vector machine regression, it did not work at all. You can see on the left that the output predicted data is consistently higher, and there's a lot of things that could be tweaked and changed and modified in the support vector machine models, and it didn't matter what parameters or what hyperparameters I adjusted and changed, it would not fit the test data at all. And you can see that in the RMS deviation turns out to be 26 cents. It's very large, even though it looks fairly linear, because it's just shifted off completely. It just didn't work at all. And perhaps it's because I'm fairly new at machine learning that I couldn't quite figure out how to make this work. But at this point in time, I'm ready to abandon the support vector machine as the predictive model for this data. So back to the algorithm cheat sheet to see what else is possible. Some of these things have very long training times, and I wasn't really interested in doing that. I have a fairly small data set, though, on the order of maybe 2,000 or 3,000 data points. And so I like the decision tree models. I think they're fairly straightforward. And one of the other advantages of decision tree models, especially a boosted model or a jungle, is that they give you feedback as to the relative importance of the different features. And I thought that that would be an interesting thing to look at in terms of which of these different pieces of the model are worth more or more important in terms of predicting the output price. So back again to looking at the performance on the in-sample data. Again, the predicted data look fairly well. They look good, like they're following the training data fairly well. The in-sample RMS deviation turned out to be really good. Sort of on the same level as the support vector machine, the quality of the support vector machine on the in-sample training data. And again, it's about 15 times better than the RMS deviation for the linear model. So it's a significant improvement on the in-sample performance. So there we go. What I said about the boosted decision tree regression is that I can look at the relative importance of the different parameters. This is a nice feature, especially when talking to business decision makers, because it allows us to do sort of a rule of thumb and give some reasoning behind the performance of the machine learning algorithms. There are some algorithms like neural networks that basically there's no way of getting out why the neural network is performing the way it is performing. But boosted decision trees in particular are nice that they do this. And so you can see that the most important variable is actually the crude price, the price of crude oil as the input to production of the gasoline, which makes a lot of sense in hindsight. When I first started working on this model, I did not include the price of crude oil as an input to the model, and it wasn't performing very well. And sort of doing more looking into what makes up gas prices, I read that the price of crude oil is important. And sure enough, it turns out to be by far the most important parameter in terms of the price of gasoline. The second most important parameter then is how much gasoline stock there is sitting in the country. This is the stores that are stored in various tanks around the country. The third most important parameter actually was slightly surprising to me. I have an input parameter where I just get which week of the year. I number the weeks 1 through 53. And depending on which week of the year we're looking at, I send that as one of the input parameters. I was thinking, perhaps there are seasonal effects, or perhaps that there are patterns in the overall pricing of gasoline. And that turns out to be the third most important parameter, significantly less so than the price of crude oil and the stock of gasoline. But it's the next most important parameter in calculating the price of gasoline, which is, again, in hindsight, the Memorial Day weekend and the Labor Day weekend, the price of gasoline goes up. And so to include that as the week parameter takes those things into account. And then the rest of the numbers just don't matter as much in terms of their effect on the relative influence on the overall model prediction. So looking then on the out-of-sample performance of the boosted decision tree regression. I'm slightly concerned about this particular model. Looking on the left-hand side, you can see that the predicted data is following the test data, but there's a lot of noise. It's actually bouncing up and down significantly more than the test data is, and that might be a sign that the model is a little overfit. But it seems to be following fairly well, even though it's a little noisier than the actual data, with the actual prices of gasoline. And the RMS deviation comes in, and it performs slightly better than the linear model on the out-of-sample data. So it's a slight improvement, but I don't know if that improvement's really worth it. In many ways, the simplest model is the best model, but because this boosted decision tree regression trains fairly fast, it was worth just keeping this model since it was slightly better in performance than over the linear model. So then putting it all back together again, what I've got is Azure Data Factory batch pipeline. And it's set up so that every week, once a week, it goes through and pulls the data tables from the Energy Information Administration's web pages, consolidates the data, puts it together as a test and data set since the training is already done. It then scores the data based on the trained model, takes that output of the scored model, stores it in SQL Server, and then the Power BI can then, the Power BI end user can then query that data on a regular basis and make decisions based on what the price of gasoline will be next week, based on the inputs from last week. And it's fairly good performance on the test data, at least. As the last couple of weeks, I finished this model, a week and a half, 2 weeks ago or so. And the last couple of weeks, the model continues to be reasonable at predicting the output of the data. I think last week it predicted a slightly higher increase in gas prices than what actually happened. But again, it was certainly the right direction as to which way we should be going, which way the gas prices would be going. And that's the sum total of this demo model that I put together. Louis, you have to tell me now, is this the point here where we can sort of take some questions and talk about, I can go into more depth or details of talking about what's happening with the model as people have questions.
Hey, Martin. I think I see a few questions here on the side.
All right, you're going to have to show me how to get there.
Yeah, it's on the questions pane. I don't know if you can see that right now while you're sharing.
Yep.
Okay. So I think the first one I see, for your linear regression, did you transform data in any way so your prediction is close to the actual?
Let me go back a couple here. There are a lot of different ways that you could do data transformations, and I know a lot of people say that to make more accurate predictions, especially for the support vector machine, that you should be scaling the data before going in. I actually tried scaling the data because the prices of the inputs. Let me see if I can go back to. Let me go back to the raw data itself. The scales of the data are all over the board, and I tried doing a data scaling where I scale everything to the average and the standard deviation, ran it through the models, and actually I didn't get anything different. So you can see the range, the gas stock. The third one down is ranged up to sort of 150 or 150,000, and then the day supply is in days, is not as opposed to barrels of oil. The refinery is in terms of percentage as opposed to barrels of oil. So there's different units and there's different scales on all of them. And I think it is actually a good idea to do data scaling, but I didn't need to because I think the parameters were all sort of close enough to each other. They weren't many orders of magnitude off that I didn't do anything different for that one. All right, so I've got another question here. At what exact date will one's own R visuals and ggplot2 become supported, available in Power BI? Okay, I don't have the answer to that one. So I got Power BI on the desktop to support ggplot2. And that was all fine, and I was really happy with that. But when I moved to the web interface version of Power BI, they said not supported, and this was last week. So unless anybody else here knows more, not yet, I guess, is my experience with that one.
And I did something.
Yeah.
Sorry to interrupt, but that's definitely right on the top of the priority list for the Power BI team. So I don't know an exact date, but I know they're currently actively working on that, making available refreshes for our images published in Power BI. So I think we should be maybe a matter of a few releases for us to see that, but not too far from now.
And it sounds like they're releasing about monthly, so it might only be a couple of months off before it's ready to go. Okay, so I'm going to keep going with sort of linear order here on questions and go until we run out of time, I guess. Except if I lose my place, in which case, okay. How effective is the correlation among variables if they have a nonlinear relationship? The correlation for a nonlinear relationship won't show. It only shows if there's a very simple linear, for example, the crude price and the gas stock, one's going up, the other's going down. If there's a nonlinear relationship, it won't show up. If there's a quadratic relationship or something deeper, it's not going to show. So I tend to use the correlation between features as sort of a baseline. If there are two features that are highly correlated, even if I don't see it in terms of linear, but if the two data points are tracking each other in a very similar way, then that means that you don't need to use both of them. I don't think there's any harm in using both features if you don't look at the correlation between them. It just is redundant data at that point. I think, I don't remember which one it was. It was something like the price of imports. I had another feature, another data set available from the Energy Information Administration that even though they didn't look like, they both looked slightly random in terms of their performance versus gas price, they were very correlated to each other. And so that ended up being a data set I didn't use in the end. The time series being, what sort of time series data is being included in the model? The trained model included everything from 1995 all the way up to September of 2015. And that what I would like to do, and this is sort of the next step with this model, is that the natural thing to do would be to retrain the model every week. So because it doesn't take significant amounts of time to do this, and I think it's fairly straightforward to do using a pipeline in Azure Data Factory, is to take the data all the way up to last week and retrain the model. And what would happen then is that the model would get better and better over time. I haven't done that yet, primarily because I got to this point and said, oh, this is good enough for now. But that would certainly be the next thing to do. That way the model every week would be updated, and I think it would do even better in terms of predicting the future prices. That way everything, all but the last week's data would be included in the predictions for next week. Can I quantify what I say an algorithm is faster than a different algorithm? All right, so on the cheat sheet, in some ways it really depends on how many features and what the length of the data, what the size of the data set is in terms of time. For 8 features and 2,000 data points, for most of these, it didn't matter. We're talking seconds on all of them, and so it didn't really matter. The only one that started to matter in playing around with it was the neural network regression, and the neural networks take significantly longer. For this kind of data set, it was on the order of 10 minutes as opposed to seconds. As the data sets get bigger, that can get much significantly longer. So I played around with some data sets where the support vector machine, the linear model takes seconds to do. The support vector machine would take a couple of minutes, and then a neural network, I would tend to not be patient enough to wait the hours that it would take to train the data. So it really depends on how much data you're looking at. Certainly, if you start with a linear regression and it takes a couple of minutes, you can expect that that is going to be several times longer as you're dealing with larger data sets. One way around that is to subsample the data. If you've got a lot of data with a lot of features, is to pick only a random sampling of that and train on that to see how well the model works. Another way to get around it would be to use a principal component analysis and do a reduction in the dimensionality of the data set, which is sort of the Azure Machine Learning has sort of the PCA anomaly detection piece up here. So there is the capability of doing principal component analysis in the Azure Machine Learning Studio. Instead of doing anomaly detection, you could just use it to shrink the dimensionality of the data set and see if that improves the timing. I haven't yet worked with data sets that are big enough that that becomes a real problem. Although even if it took, you know, a few hours to a day to do a training set on a once a week basis, that's actually not that bad. So that's kind of the time scales that I'm talking about, my experience here. Did I consider adding other features such as weather and events and so forth? I did. I guess that would be the next step. Pulling the data from the Energy Information Administration was a sort of countrywide averages of the gas prices. And I think really to make a bigger impact on the models would be to narrow it down to regions. They actually have a regional version of the data. And for example, I could look at what would be the impact of the hurricane season on gas prices, or what would be the impact of flooding in California on gas prices. Because it's going to affect production, or in the Gulf of Mexico when oil rigs get shut down. In this model, that got taken into account based on the production, the fraction of refineries that are producing. But that would be another piece that could be looked at in this model. I would probably do the same kind of thing. I'd pull the data off in the first step of the pipeline, in the first activity, and then join it into the data using Pig on Hadoop to join the data together and then just train with that extra pieces of data. I took into account the events by looking at sort of week in, week out, and the week of the year, at least recurring events. Anomalies such as the effect of a terrorist attack on the price of oil would be another step to go, and perhaps there would be a way of pulling in the Twitter feed and looking at the overall impact or the positive or negative reviews that might show up following some kind of major event that would impact the price of oil. Okay, so the next question here is, the data seems to be fairly straightforward. What about mismatch, random, unrelated data, bringing it together, incorporating it? Yeah, so I think the hard part is decide how to piece the data together in the early stages. I think it looks more straightforward now, sort of after the fact. But early on, there's a question as how to aggregate, sort of daily calculated versus weekly data points versus, random data points that come and go versus filling in missing data. There wasn't any missing data I didn't have to fill. All of that data cleaning has to happen early on. And sort of going back to I'm not sure which way is the most straightforward way to go on this. Going back to the pipeline to look at it, let's see if I can go that way. To look at the pipeline and say, all right, early on, if I've got missing data, what I can do is fill that in either using a linear interpolation or sampling down the overall features that I have. And that would all happen in Pig, where I'm going to use some of the user-defined functions in Pig that will do some of that data cleaning for me. And there's decisions that have to be made. And depending on the use case, I would choose one method or another method. If it looks like it's a fairly linear data set, I might interpolate between them. Or I might turn one of the data sets into a factor as opposed to a continuous variable. And the nice thing with factors is that I can turn them on and off. I could say this factor is not showing for most of the data points, and then when some event happens, I can turn the factor and set the factor at true, and then the factor then matters for that week. And then the model will train, and Azure Data, their machine learning studio handles factors just fine. And so what will happen is that as the factors turn on and off, then it will account for that in its predictive model. The nice thing about boosted decision trees work really well with factors. If the decision tree basically splits the data and asks what's the best way to split it to minimize the entropy. And if you have a factor that turns on every time the data price goes up, then it will find that very quickly and use that as an important feature. So I think that's how I would handle mismatch or random data. The unrelated data is a little harder because if I don't know if the factor matters or not, start with it in a model, and it's always easy to take out features and retrain the model, especially if retraining the model only takes a couple of minutes. That's fairly straightforward. So if it's unrelated data, then I might be easy to find that at the end. So a question about the correlation analysis, was it based on raw data or transformed data? That was just the raw data I used for the correlation analysis. I think our correlation function has a scale in it, so I don't know that I have to do that by itself. Can I show again how to choose different machine learning strategies in Power BI? Okay, so this was something that I decided I had to decide whether or not to implement all of this many times or to do it just once. So what I ended up doing was only a single machine learned strategy in my pipeline. And so I actually only have the boosted decision tree regression as the output for takes the data and puts it in SQL Server that I can then query from Power BI. The other models I have in the R notebook in the Machine Learning Studio, but I don't have them integrated into Power BI, so I can't switch back and forth in there. It's something I thought about doing it, but it would again be another 3 steps in the pipeline, so I'd have to train on all 3 models, and I got to the point where I was too lazy to do that. So I think I've got through most of the questions. If there are any other questions coming in here towards the end.
All right, looks like that was it. Hey, Martin, thank you so much again for a great presentation, and thank you, everybody, for attending. Just so you know, be on the lookout for an email from the vertical chapter. We have another presentation next Friday. We'll have Mark Tabladillo tell us about data science at Microsoft and the different initiatives that they have. So once again, thank you so much for joining, and have a great weekend, everyone.
Great, thank you.